Okay, so last Thursday, was our Unit 3 test. Those of you that have it turned in, it is graded and in the book for you. So please double check the grade book. If you don't have a grade, you need to get that resubmitted so that we. Unit 4, starting today, we are officially, well, not quite. We will be officially 2/3 of the way through the course at the end of this week, so we're coming up on it pretty fast here. Unit 3 dealt with the measurement units and converting from one unit to the other. Unit 4 deals with making the measurements and the theory of measurement. And then some of the measuring devices we'll deal with. And then there's a little bit of algebra in there with it as well to round off the unit. Today we want to talk about a ruler. Now I realize that most of you pretty much know how a ruler works, but I want to start off with how it works in order to get into some of the finer points of the concepts behind it.
I can't hear you.
Oh, let me take a look here, make sure everything is.
Nope.
How about now? Can you hear me? Is that any better?
Hello?
You can't hear me at all? You may have to log
Not
out.
on my end.
What's that? No? You may have to log out and log back in. Here, let me. Okay, the rest of you guys can hear me okay? Any better, Sean?
Yes, we can. We can hear you.
Okay, perfect. Okay, so a ruler has a beginning end, zero end of the ruler. And to measure an object, we would line it up with that zero end, that beginning end. So our ruler typically has our measurement unit marked out on it. We're not going to name a particular unit here, but we'll just label it off here. So we may, if we're measuring that blue line right there, blue object, whatever you wanted to call it. Try to label it just a little bit differently. Greater, spaced. Right now, when you look at it, it's between the 3 and the 4. It's closer to 4 units. So if we were measuring that blue object, we would have to call that 4 units long. Now, some of people might say, well, it's about halfway between. Can't we call it 3.5? And the answer there is no. We cannot call it 3.5 because there is no marking at 3.5. Only go to the nearest actual marking on our measuring device. I might have another piece like this green line. That green bar or green object would also measure 4 units on this device, on this ruler. Obviously, the green and the blue are not the same size, but this ruler is not capable of distinguishing between them. Concept of precision. The ability to distinguish between similar objects. These two objects are very similar in length. Oh, my handwriting is horrible. The objects are very similar in length, but they're not the same. But this ruler here cannot distinguish between them. Both of them measure up as 4 units on this ruler. So how can we make it more precise? Well, the simple answer there is make smaller divisions. Our units are already made. We can't change our units and make them smaller, whether it's an inch or a centimeter or whatever. The size of the actual unit is determined, but we can make the division smaller by going a fraction of a unit. And that's exactly what they did, is they came through and they said, okay, we're going to mark a spot right in the middle here. That's going to be our half unit. Now, unfortunately, for our blue and our green object, both of those are still closer to 3.5. So even by increasing the precision on this object, this ruler, is still not quite precise enough to distinguish between the green and the blue object. So how do we make it more precise? Cut those in half again. We're going to a quarter of the unit. Now we can distinguish between them. The blue here is 3.5 units, while the green is 3 3/4 units. So we have now reached a level of precision that allows us to distinguish. That is the degree of precision. Degree of precision is literally simply the smallest division on the ruler. So on this ruler, the degree of precision would be 1/4 of a unit, whatever those units are. That is the smallest division on our ruler. Now, if we look at these objects that we measured here, the blue object is not exactly 3.5 inches. It's between 3.5 and 3/4. It's just closest to the 3.5. On this ruler here, anything that would have been between here and about here would have been measured at 3.5 inches, because we're going to the nearest marking, which means it could be off up to halfway to the next marking. That is what is called the possible error, or simply the error in our measurement. Error is built in. It's part of the device, the divisions. And that possible error, the full name, I'll just call it the error, but it's really greatest possible error. And by greatest possible error, I mean that's if human error is out of the question, everything is done as correctly as it possibly can be. This is the biggest that the error in the device could be. And it is simply 1/2 of the degree of precision. It's halfway to the next unit. The degree of precision is the distance to the next unit. So for this ruler, that possible error is 1/2 times 1/4 unit. That possible error works out to be 1/8 of a unit. So if we look at this measuring device, this ruler, I guess we would call it. Degree of precision here. Remember, it is the smallest unit on the measuring device. So this is, usually I don't go right at the beginning end because that end is often worn or whatever. I usually look at 1 inch and I go from there. That smallest unit there. To determine how big that smallest unit is, I have to figure out what the divisions are on this ruler. I will go from one clearly marked spot, which is the 1 in this case, to the next clearly marked spot, which would be the 2, and I count how many divisions there are. Now, I'm not counting the lines, I'm counting the spaces. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. There are 16 divisions, which means each of them is a 16th of a unit. Now I'm going to just say this is inches for now, so it's a 1/16 of an inch. Obviously, there's a shortcut there. You could have counted, we had 4 here, and each of those spots is the same size, so it'd be 4, 8, 12, 16 if you wanted to count them that way. So our degree of precision here is a 1/16 of an inch. That is our smallest division. So our possible error, again, this is not the person using the ruler screwing up. This is if the ruler is used perfectly and just an object happens to fall between divisions. The possible error here is 1/2 a degree of precision. So 1/2 times 1/16 inch comes out to be a 32nd of an inch. Now the proper way we should list that, we should list it as plus or minus a 32nd of an inch, because it could be smaller or it could be larger than the actual measurement. The actual object, I should say. So I'm going to give you an example to try in your notes here. I want you to here find.
Hey, I'm back, and I can actually hear you.
And possible error. Give me about a minute.
Sorry.
Take a look, see if you can figure those out from the ruler, and we'll go over just a little bit.
Todd, I'm sorry for earlier. I was having technical difficulties.
That's what you get with technology, no problem. So our precision is our smallest division again. So again, I don't usually start at the first end here because usually those markings are a little worn or hard to see, just rounded ends or whatever. So I'll go up to 2 clearly marked divisions. I've got the 1 and the 2 inch. I count the number of spaces between them. 1, 2, 3, 4. Now I can just double it because I know I'm halfway, but I'll count them all. There's 8 spaces there, which means each of those spaces, 1/8 of an inch. So that's my degree of precision. My possible error, again, is half of that degree of precision, because if it's halfway to the next piece, it's going to be counted. Like this would be halfway to the next division, and that's halfway to the other one. That still be counted as 1.5 anywhere in that range. So 1/2 times the degree of precision is the 1/8 inch. That gives us 1/16 of an inch. Plus or minus 1/16 of an inch is our possible error. So if we measure something, and the measurement on this device comes out to be 1.5 inches. It could be a 1/16 of an inch shorter or a 1/16 of an inch longer, which means that every measurement has what we refer to as an implied range. An implied range, again, is based off of the precision of our measuring device. If this was a 1.5 inch measurement, the implied range goes from the measurement minus that error, hence the plus or minus there. So it'd be 1.5 inches minus a 1/16. Now I'm going to trust at this point that you guys can do the common denominator to make, and then the subtraction to get that to come up to 1 7/16 inches. 2 larger number that would be the measurement, the other end of our implied range, be our measurement plus that error. So again, we take our 1.5 inch measurement, and now we're going to add the 1/16 of an inch of error, possible error. Once again, I'm going to trust that you guys can do the common denominator and add to get to that as 1 9/16. So with this measuring device, with this ruler, the degree of precision of an 1/8 inch, meaning that it goes down to 1/8 of an inch is the smallest division. If an object measures 1 1/2 inches, that's actually saying it's somewhere between 1 7/16 and 1 9. So to find the implied range, if I have a measurement of 3 3/4 inches on a ruler with a degree of precision of 1/16 of an inch, goes to a 1/16 of an inch. Find that implied range. Well, the first thing I have to find is that possible error. That error will be 1/2 times our degree of precision. 1/2 times the 1/16 of an inch is plus or minus a 32nd of an inch. So then our range, we take our measurement minus a 32nd of an inch, which is going to be what, 24, 23, 3 and 23 32seconds. To our measurement plus a 32nd of an inch, which will be 3 and 25 32seconds of an inch. That is the implied range. Now, many measurements in construction and stuff like that, they still use the fractional inches and fractional measurements. But you get into machining, technology, any mechanical, auto mechanics even is going decimal. Any of those mechanical fields, most of the measurements are decimal inches rather than fractional inches. By the way, we kind of got to it at the beginning here, but I didn't really point it out. Why is it that the traditional inch is not divided into tenths? And why is it divided into halves and quarters and eighths? Tenths would have been a lot easier. Well, the reason is, if this is my unit of measure, and obviously this is exaggerated, it's large, and I want to cut it at something smaller, cutting it into 10 equal pieces is tough to do. But to cut it into 2 equal pieces or cut it in half is very simple. I just fold it. That's a perfect 1/2 inch, the perfect midpoint. Want to make it smaller yet? I fold it again. There's a perfect quarter. So that's why we ended up with halves, quarters, and eighths, because it was very easy to divide it perfectly into a half a unit or a quarter of a unit, and so on. Now we have better technology. We can divide it up very evenly into tenths or hundredths or whatever. So we do. It was just simply a limitation of their capabilities that caused them to do it that way. So if we are using decimal inches, which means we would be using tenths or hundredths of an inch, or even metric, we could be using tenths or whatever of a centimeter or however. Decimal place is going to tell us something. If I tell you that something is 4.2 inches, or if I tell you that it is 4.20 inches, that's saying the same thing. Well, mathematically, yeah. 4.2 and 4.20 are the exact same number. That 0 at the end adds no value. But measurement-wise, there is a difference. There's an implication about that degree of precision. This 4.2 inches is implying that we had a measuring device that was only capable of measuring to the nearest an inch. And whatever it is we were measuring, closest to 4.2, so it's somewhere in this range here. So this would imply a degree of precision just going to put precision rather than the whole degree of precision. To imply a precision of only 0.1 inches, which implies error of 1/2 times 0.1 inch, which would be plus or minus 0.05 inches. So this is saying that our range is anywhere from 4.2 minus 0.05, so 4.15 inches, to 4.2 plus 0.05, or 4.25 inches. That's not a bad range, but let's look at what this is implying over here with that extra 0. That is implying that our ruler actually was divided to the nearest 100th of an inch, and it was still closest to 4.2. In other words, it's implying that we are somewhere in that range. It's implying that we have a degree of precision of 100th of an inch, 0.01 inches. Which then implies that our error is half of that. 1/2 times 0.01 times, by the way, inch gives us 0.005 plus or minus 0.005 inches as our error, which implies a range. 4.2 minus 0.005 is 4.195 inches. To 4.2 plus 0.005 of 4.205 inches. That is a much smaller range. So we cannot just put this 0 at the end here unless we really need it. What I mean is unless the measuring device really was capable of measuring to 100th of an inch, we can't put that 0 there. Truly only measured to 1/10 of an inch, then we have to leave it as just 4.2. If it really did go to 100th of an inch, then we should do 4.20. So that whoever is reading that measurement knows that it really was to that smaller unit. It really did go to 100th of a unit. Metric measurements, of course, are always going to be decimal. So if I give you the measurement 3.74 centimeters, it is implying a degree of precision of whatever the place value is of that last digit. This last digit is the 100th. So it is implying a degree of precision of 100th of a centimeter, or 0.01 centimeters. Which means our possible error, 1/2 times 0.01. Now, to make this easier on ourselves, we could do 0.5 instead of 1/2 times 0.01 centimeter, which is going to give us plus or minus 0.005 centimeters. Which means the range, the implied range of that measurement, is from 3.74 centimeters minus 0.005, which is 3.735 centimeters, to 3.74 centimeters plus 0.005 centimeters, or 3.745 centimeters. Now this is kind of a tricky concept. It's not a way you're used to thinking. If this were a more formal math course, or if it were a physics or an engineering course, we would talk about something called significant digits. In other words, digits that tell us something about the number. Up here, this 0 is considered a significant digit because it tells us that we actually did measure down to that 100th of an inch. It's important. It tells us something about the measurement. That's what a significant digit is any digit in the number that tells us something about the measurement. Gives information about the measurement. That's really all we're doing is looking at the number and making sure that the number we write accurately describes or portrays our measurement. That's why we didn't put a 0. If we had put a 0 on the end of this, that would have totally changed the meaning of that measurement. The degree of precision would have been different. It would have been 0.001 centimeter. And then the error would have been different. It would have been plus or minus 0.0005 centimeters. Well, that's not the truth. Our measuring device really could not go down to 1,000th of a centimeter, so we didn't put that 0 on there. So making sure that we know that when we write a measurement, we don't put extra zeros in unless we need them, unless they really are part of that measurement. In fact, second thing we need to get out of this is when we read a measurement, those implications should be there. We should first ask ourselves to make sure we do understand, is that really what's implied here? Did whoever wrote this measurement understand that that's what they were implying? Or is that those digits in error or whatever? Like I said, we're not going to get into the actual counting of significant digits themselves, but we do need to understand what is precision and how the precision of the measurement plays into the error. And we're not going to, like I said, we're not getting into significant digits, means we're not going to get into rounding numbers and add them together. But we should be aware, if I have a measurement like, 6.3 inches, and I'm adding to that 0.02 inches, is that really something valid to do? Mathematically, sure. 6.3 plus 0.02 is 6.32. However, the error in this measurement, precision is to the 10th of an inch. Error is half of that precision, or 0.05 plus or minus 0.05 inches. When I look at it that way, this error of this measurement of the 6.3 inches plus or minus 0.05 of an inch is bigger than what we're trying to add to it. So it's not appropriate to try to add 0.02 of an inch to 6.3 inches because the error in one measurement is larger than the error of the other. So using this, it helps us be aware of combining numbers that shouldn't be combined, where they're not on the same scale. The technical term is order of magnitude. 0.02 of an inch is on a totally different order of magnitude than 6.3 inches. Like I said, a more formal math course would talk about that significant digits and where do you round? When you add two numbers, where do you round your answer so that it's honestly portraying how accurate it is? That's a pretty tough concept. We're not going to get into it here. But be aware that is how they determine when they're calculating with measured numbers. They use that idea of that precision of the number to figure out, after I calculate, where should I round this to so I'm honestly portraying the capability of the measuring devices used in this. Right now, we'll give you your first homework assignment here of Unit 4. This is back in the book. Page 173, exercise 4.2, problems 1 through 29 beyond. Be prepared for tomorrow. There is a packet, it's posted on Blackboard, a packet on reading calipers. A few different styles of calipers are out there. So be aware of that. We will be going over that in class tomorrow. So with that, you guys have about 18 minutes left to start on the homework. I will shut up here and I'll be on the network if you have any questions you need to ask. Otherwise, that is our